14.6, triple integrals. So these are going to be very similar to what we did back when we looked at double integrals. So I'm just going to quickly, so I first, I guess, looked at integrals with one variable. Then I did it double integrals. So a single integral, double integral. Now we'll look at a triple integral. So first, partition of a closed parallelepiped, let's say R, which is the Cartesian product of the closed interval from A to B, Cartesian product with closed interval from C to D, Cartesian product with the closed interval from E to F. Let P sub x be a partition of the closed interval AB, P sub y be a partition of the closed interval C to D, P sub z be a partition of the closed interval E to F. Let x sub I minus 1 and x sub I be in the partition P sub x. Let x sub I minus 1, x sub j minus 1, let y sub j minus 1, y sub j be in the y. Let z sub k minus 1 and z sub k be in the partition for z. Oops. Let R sub I, j, k be the Cartesian product of the closed intervals from x sub I minus 1 to x sub I, Cartesian product, y sub j minus 1 to y sub j, Cartesian product with the closed interval, z sub k minus 1 to z sub k. And let delta of R sub ijk equal the product of x sub I minus x sub I minus 1 times y sub j minus y sub j minus 1 times x sub k minus, times z sub k minus z sub k minus 1. Let omega equal the set of points, choice points, omega 1, 1, 1, 1, omega 1, 1, 2, dot, 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 all the way up to omega. I guess these will have, for this partition of x, they'll have m subintervals, for y, n subintervals, and for z, p subintervals. So this will go to omega, the choice point, MP in MNP. Where, and that's why I tell you, where the number of subintervals of the partition of x is m, the number of subintervals of the partition y is n, and the number of partitions of the variable z is p, where each omega sub I, j, k is in this R, I, j, k rectangle. Let, or parallelepiped, let F go from R3 to R. Let M sub ijk equal the inf of F sub x, F of F at x, for x being in this rectangle, this region, the parallelepiped, ijk. Let capital M sub ijk be the sup of f of x, where x is in this ijk parallel pipet. Let P sub xyk, xyj, xyz equal the partition of x, Cartesian product partition of y, Cartesian product partition of z. Let the norm of the partition, the mesh of the partition equal the sup over ij and k of delta r sub ijk. Let the lower Darboux sum L of the partition P, X, Y, Z, F equal the sum over ijk of little m sub ijk delta r sub ijk. Let the upper Darboux sum U, P, the partition P, X, Y, Z at F be defined as the sum over ijk of capital M sub ijk delta r sub ijk. Now that I told you Darboux, Riemann integrability. So I told you what the upper and lower Darboux sums are. Let's first do Riemann integrability, then we'll do Darboux integrability, then I'll state that they're both the same. So Riemann integrability over the parallel pipet R, and if the real number, and we'll denote the real number by the triple integral over R of F, exists such that for every epsilon greater than 0, there is a delta greater than 0, such that the norm of the partition being less than delta implies that the absolute value of the difference between the Riemann sum, the sum over ijk of F at omega ijk times delta r ijk minus this number, which we denoted by this triple integral over R of F, is less than epsilon for every choice point in this set of choice points, then F is Riemann integrable over R. So I already told you what from above, what a partition this was defined as, and I told you what this was defined as. So I'm using the same notation and what each of these were defined as. So I'm using the same notation as in the previous paragraph. Darboux integrability over R. If there exists a unique real number, and again, we denote it by the same notation, the triple integral over the region R of F, such that for every partition, P sub XYZ of R, the lower Darboux sum of this partition for F is less than or equal to this number, the triple integral over R of F, which is less than or equal to the upper Darboux sum for any partition, P for this function f. Then f is said to be Darboux integrable over R, i.e., in other words, f is Darboux integrable over R if there exists an epsilon greater than 0, such that there exists, if for every epsilon greater than 0, there exists a partition P sub xyz, such that the upper Darboux sum relative to this partition for f minus the lower Darboux sum relative to this epsilon. Okay, and I should say that Riemann integrability and Darboux integrability are the same. A function f is Riemann integrable if and only if it is Darboux integrable. Okay, so they're both the same. So maybe I'll say that. Riemann integrable if and only if Darboux integrable. So I should note that these are the that there's a relationship between the two. Well, that they're the same. So, well, even though the concept is different, anytime you talk about Riemann integrability, any function that's Riemann integrable over any region will be Darboux integrable over the same region, and vice versa. So they're really the same. It doesn't give you anything more or less. So both Riemann integrability and Darboux integrability give you the same restrictions on what your functions are for integrability. Fubini's theorem. So Fubini's theorem holds, well, for triple integrals. If the triple integral over some region of the absolute value of f is less than infinity, then the triple integral over that region, doing the iterated integrals in any of the, probably 6 of them, 9 of them, 6, any of the 6 different ways that you can do the integral. So doing x, y, z, y, x, z, x, z, y, z, x, y, z, y, x, y, z, x. So any of those ways of permuting the order of those 3 integrals will work, so long as this is true. And of course, we showed that for a double integral, of course for a triple integral, it'll be the same analogous thing, that that you can show you have to be sure that that this condition holds. Otherwise, it may not be true. Note that we can just say that this holds if f is continuous on the region, except for a set of measures 0. And so, so long as something is a function is continuous almost everywhere, then you can talk about these iterated integrals. So let me just sort of say that you can have iterated integrals of type 1 and type 2. And so the basic idea, I won't write them all down, So I just sort of said etc. I mean, they're all of those types for all those 6 differing integrals that we looked at. So if I can write my region such that, well, the region that I'm integrating over be restricted to, so let's say I'm somehow integrating over this type of region. Okay, so that for X, it just lies between A and B, and I can find curves relating the other ones. Then I can, is Fubini's theorem? Yes, it's identical. So this Fubini's theorem is identical to what we wrote for our double integrals. So, I mean, the only difference is that instead of a double integral, it was a triple integral. There's really no difference. And similarly with iterated integrals, what I'm writing here is the same for triple integrals as it was for double integrals. So the idea is as follows. So I won't write them all down, as I say, because you have to do it for all 6 of those integrals. But the idea is as follows. If you can somehow write down this region that you're integrating over in a fashion so that it's bounded by curves that only depend on functions that you haven't integrated, only with variables that you haven't integrated yet with. And so if I integrate here first with z, then my limits of integration can depend on x and y. If I've integrated with respect to z, and so notice that they have 2 variables here, x and y I can still vary with. If I integrate here now with respect to z and then try to integrate with respect to y, well, there's only one thing left that can vary, which is the x. If I then try to integrate that again, well, there's no other variables here, so these have to be constants. So here, if I integrate, oh, well, it's going to be the same thing. I can integrate where my limits of integration depend on x and y. Then when I integrate the second one, well, it can depend on y. Then when I integrate the third one, well, there's nothing else left, so they have to be constants. And that's the basic idea for iterated integrals. The limits of integration can depend on things that you have not yet integrated, but it can't go the other way. So at the end, so that at the end you get, so the idea is at the end you want a number. Of course, later on we may not want to, but that's the idea. If this thing here is just some fixed region, then this has to hold. So if it's a fixed region, then you want that this comes out to a number. Okay, so we have the same applications that we had from 2 sections ago. So the volume is just the triple integral, the volume of the region E is a triple integral over E of 1. If you have some density that depends on 3 variables, x, y, and z, to find the mass, having some density, rho, for some region R, will just be the triple integral over R of rho. Same as before. If you want to find the moment about, well, the non-x axis, it'll be the triple integral over R of x times rho. If you want to find the moment about the non-y axis, moment about the y x z plane, then it will be the triple integral over r of y rho. If you want to find the moment over the plane that does involve z, so the non-z plane, then it's the triple integral over r of z times rho. And the center of mass will be a half coordinates. X bar is being the moment over the thing that that doesn't include the x over m. Bar as the moment about the non-y axis over m. Z bar equaling the moment about the non-z axis over m. The second moment, the moment of inertia, about the x-axis, triple integral over r of y squared plus z squared rho, over the y-axis, the moment of inertia about the y-axis, triple integral over r of x squared axis. So the moment of inertia about the z-axis, the triple integral over r of x squared plus y squared rho. Suppose you have an electric density, sigma, at each point in some region R. Then the total electric charge on the region R is just the triple integral over R of sigma. A probability density function is a function such that f is greater than or equal to 0, and the integral over R3 of f is equal to 1. The probability that that your point is in some region E is the integral over E of this probability density function f. Okay, so if you notice, all of these are very similar to what we've done previously. So let me do an example. Let me do a problem, an exercise. Let's see if I can move. Okay, stop. Okay. Sorry, I'm just sort of stuck here. There. Okay, so now I have enough room. Well, at least some room to do this. Okay, so I want to find the triple value of the triple integral E sub evaluated at yz dv. Over where E is actually written really nicely. So I don't even have to draw this because they've already given us everything we know. So this is a y, goes between 0 and 1. X goes between y and 1. And z goes between 0 and xy of E of z over y d z d x dy. Okay. Since they gave it to you so nicely, it's just really easy to do it in this fashion. So they've already given us a region where they've done the work for us. So if they've done the work for us, we might as well just use what they've done. If, like in the double integral case, if you find that after you've done, as you're doing this, that you come out with an integral that is really difficult and you can't do, then you may think about changing the order of integration. And so if it turns out that you get wood, all of a sudden, try to rewrite this or whatever. But in this case, I don't have to because it's done nicely for us. Okay, so let's integrate. First, let's integrate with respect to z. Oh, good. So the integral with respect to z, the integral of e to the any exponent is e to that exponent. As long as this exponent is a constant times your variable, divided by the variable with the constant, which in this case is y. Evaluated, where z from z equals 0 to z equals xy. Oh, that'll make my life easy. Dx dy. So this triple integral is no worse than what you did with a double integral. It's the integral from 0 to 1, y to 1. Plug in for z, x, y. So this is y, e to the, well, the y's cancel, so x. Plug in 0 for z, so 1, this will just be y, dx, dy. So let's integrate this. With respect to x. So the integral of e to the x is just e to the x times my constant y. The integral of y is just going to be, well, the integral of the constant y is just going to be x times the constant y, where I'm evaluating from x equals y to x equals 1. Okay, so let's plug those. Let's plug those values in. Integral from 0 to 1 of plug in x equaling 1. Oh, so that's y minus y. Plug in y minus y to the y minus y squared. Dy. Okay, so this is equal to not much I can really simplify there. Maybe I'll just write this as y e minus 1, so that's a constant, minus y e to the y plus y squared dy. Let me get some more room here. So let's integrate this. The integral of y is just 1/2 y squared times the constant e minus 1. To integrate y e to the y, well, there's several ways I can integrate it. One technique would be just to do integration by parts. And so if I do integration by parts, I get a minus. Well, or actually I can just sort of guess the answer and then check it. So let's guess the answer. So I'm just using the fact that the solution space to the integral of y e to the y has to involve y e to the y, a constant times y e to the y plus a constant times e to the y. So let's see. Let's try this and see if this works. Okay, so let's just check that, see if that works. The derivative of e to the y is just e to the y. The derivative of this term would be by the product rule, e to the y, which cancels with that one, minus another y e to the y. So it's just minus e to the y. So that's correct. So just sort of guessing the answer, I get this form, plus the integral of y squared is 1/3 y cubed. And I'm going to evaluate that between 0 and 1. Okay, so I plug in 1, and maybe I'll just write it. I plug in 1, 1, 1, 1, and then 0. That gives me 0, 0, 1, 0. So a whole bunch of zeros, except for that. Okay, so this is equal to 1/2 e minus 1/2 minus e plus e, those cancel, 1/3 minus 1. So this is equal to the e's cancel. Okay, so that's 1/2 e. And there'll be a minus. Let's do 6. So 2, 6, minus 3, 6, minus 6, 6, 2 minus 6 is a minus 4, minus 3 is minus 7 over 6. And that is your answer. Okay. Let's do an example. Okay. Well, I'll do that. Okay, so, and maybe I'll actually put some stuff up here. Let's see if okay, I'm just sort of lazy with, I don't want to have to redraw this stuff again. Okay, so even though I don't know how good the drawing is, but okay, so find the volume of, okay, so find the volume of the solid bounded by the parabolic cylinder z equal 4 minus y squared and bounded below by the elliptic paraboloid z equals x squared plus 3 y squared. Okay, so you're going to have to sort of, I'll try as best as I can to explain this sort of drawing that I've done. Here is a parabolic cylinder. So it looks like a parabola that's sort of been, it looks, I was going to say like I don't know, a saddle, but without the things coming up. It's think of this as being sort of like a sheet of metal that you've bent. So it looks like a parabola uh, in one, if you slice it in one direction. So if you slice in one direction, is a parabola, but in the other direction is just sort of curves to that sort of sheet of being a parabola. Okay. So I want to, and then suppose I have this below it is a elliptic paraboloid. So this is some sort of elliptic paraboloid here. So I have, it's this thing in red. If you look, it's a elliptic, it's a parabola. So in one direction, it looks like a parabola. In the other, so it's let's see if I can draw it bigger. So it's a parabola, but so think of this as being, if you took a paraboloid, take a parabola and spin it, but when you spin it, you spun it so fast that it sort of bulges out in one direction. So it's not quite it's symmetric if you sliced it in. It's not fully symmetric around the whole circle. So here, so it keeps looking, so for each of these, it looks like an ellipse. So this is an ellipse here, and this is a parabola. Okay, so that's, we want to find the volume of that, but this intersects, this is what I'm trying to draw here, this guy here intersects in the other direction this guy. And so it's only this part of, so it's not this full region on top. It's just what it intersects here. Of that, where it intersects with that parabola, this part of this region. Okay, I hope you can sort of understand this orbital drawing. But that's what we're trying to, what I'm trying to figure out the volume of. It's this parabolic ellipse here that's within a cylinder. Okay, so that's what I have. So now let's look at this down the top of that intersection between the parabolic ellipse, parabolic cylinder. Well, I'll get something, and so I'll try to project this down, and I'll try to figure out what that is. Okay. So I want to find the equation where the parabolic ellipse and parabolic cylinder intersect. So I'll try to find that. So I've actually, well, I want to sort of justify this. Okay. So let me get another page here. So I have the parabolic cylinder. And I have the parabolic ellipse. So where they intersect is, well, where I have that 4, oops, minus y squared is equal to x squared plus 3y squared. Okay. And so they'll be intersecting at that. And so let's add y squared to both sides. So this is x squared plus 4y squared equaling 4. I can divide by 4. And so this is x squared over 4 plus y squared over 1 equaling 1. So this equation here is actually the projection into the xy plane of this intersection. Okay. So let's see if I can. Okay, so I'm trying to figure out this red sort of parabolic ellipse, the volume of this red parabolic ellipse, if you can sort of see the red here. And what I've done is I've now shown a light down, and the shadow of this region is this projection, which is an ellipse centered at the origin in the x. It's an ellipse in the xy plane, centered at the origin, having a radius of 2 in the x and 1 in the y. And so, voila, here it is. And so it is an ellipse. So this is an ellipse. Okay. And so it's some ellipse. So centered at the origin, it has a radius here in the x direction of a 2, and a radius, even though it doesn't quite look like it, it's supposed to be more squashed out. This is supposed to be 2, and that's a 1. They almost look the same. But this is supposed to be twice as long as this guy. I don't really care. It's just a drawing. Okay, so this is the equation of my ellipse. I can write it as follows. I can solve for y. And so if I solve for y, well, there'll be a 4y squared equals 4 minus x squared. Take the square root. So you get a 2y is equal to plus or minus the square root of 4 minus x squared. And so y is equal to plus or minus 1/2 rad 4 minus x squared. So this red part I've denoted as the upper half, the 1/2 radical 4 minus x squared. This, maybe I should actually interchange these, the order of these, because maybe that looks better if I do that. Okay. Because this is what I was trying to find the volume of. I think that's a better way of writing it. Okay. For control, oh well, can't go any further down for some reason. Okay. That's good. Okay, so this projection here of this intersection between the parabolic, the elliptical paraboloid, and this parabolic cylinder is this here. And so above it, so at each point above it, it has a height. It has a height in the z direction of, well, this parabolic cylinder. Okay, so let's try to find the volume. So now, so I'm just sort of at each point, let's see if I can do this without making too big of a mess. So at each point in this, say each point here inside, each point here inside of this ellipse, it goes up until it hits the parabolic cylinder. Okay, so let's find the volume. So the volume, and maybe I'll just sort of abstractly say the volume, is some integral over this region of, well, 1 dV. Okay, so now let's try to figure out what it is. Okay, so, well, let's figure out duration. So let's do TZ. Let's do it this way. Okay, not the X and Y making difference, but okay, so I'll first figure out the limit integration for the X. And so for the X, well, it's just going to be minus 2 to 2. Remember that this went out in 2 in X and 1 in Y. So limit integration here are plus and minus 2 for X. So for the X, it's plus and minus 2. Okay, good. So I've done the X. Now I want to do the Y. Okay, so now what is Y in between? And it's Y as a function of X. So my limits of integration can be a function of X. Okay? So, so I'm going from here to here. From this guy, which is a function of X, to this one, which is also a function of X. So I'm okay with that. So that's a minus, what was it, 1/2 of 4 minus X squared. And a 1/2 4 minus X squared. Okay? And so now Z can depend on both X and Y. So I'm okay with Z being a function of X and Y. Okay, so let's do this. So let's figure out where you're going from. Well, you're going from this elliptic paraboloid to this parabolic cylinder. You're going from this guy here to this guy. So you're starting, so this is the upper part. This is the lower part. It's bounded below by this and above by this. So, and notice that these are that now I have Z as a function of X and Y. So I'll just do that. Here's my integral. Good. So this is x squared plus 3y squared and 4 minus x squared. 4 minus y squared, sorry. And this is, I'm integrating just one, and this was z, y, and then x. Okay. Any questions on how students have, this is the hardest part for students, is how to figure out this first step. Once you integrate, it's easy. Does everyone understand how I got this integral, the limits of integration? Okay. Okay, so far so good. So you'll have to do practices on these. The only way to do this is to keep doing it several times, and then you'll figure out how to do these. Okay, so let's integrate. So this is integral from -2 to 2 minus 1/2 4 minus x squared plus 1/2 rad 4 mirrored. I don't know. Integral of 1 is just z, evaluated between z equals x squared plus 3y and 4 minus y squared. So dy dx. Okay, good. So let's evaluate. So again, the same limits of integration. As before. Nothing has changed yet. Okay, so now let's plug in z equals 4 minus y squared and x squared minus 3y squared. Simplify that. Minus 2, again, same limits of integration. Minus 1/2 rad 4 minus x squared plus 1/2 rad 4 minus x squared. And so you just get a 4 minus x squared minus 4y squared. No, plus 4y squared. That's a plus 4y squared. That's a plus 4. That's a minus and minus become a plus. Shouldn't that have been a, okay, that's a 2y squared. Ooh. Okay. I was remembering it from the intersection from before. That's why I plugged in a plus, a minus there, which should have been a plus. So that's a minus 4 y squared minus x squared dy dx. Okay, good. So now we can integrate this. So this is equal to integral -2 to 2, integrating with respect to y. And so the integral of 4 is 4y. 4y squared is 4/3. Ooh, y cubed. The integral of x squared is just x squared y. Evaluated at those limits of integration. And this is y. Okay, so actually this is odd, so that's good. So since this is an odd function, we just have to double. Plug in, say one of the upper limit, and then evaluate the lower limit will give you the same thing, except the sign will be changed. So I can actually say that this is going to equal. Let's see if I can do this. Okay, so this will be the integral from -2 to 2 of 4 times, well, I wonder if I can say this. So when you plug in, what I'll do is I'll just say at the end. So plug in y, so it's a half, and then it's the square root of 4 minus x squared. Minus 4/3. Plug in a half cubed is 1/8 times 4 minus x squared to the 3/2 minus x squared times a half, times a half gives me minus 1/2 x squared rad 4 minus x squared. Now, if I plug in the value at the minus, the same thing, by the fact that that each of the y's have an odd power, that's just going to double. That'll be the same amount. You'll be subtracting the negative of it. So you'll just be adding these. So this is just going to be double this amount. Okay? And so let's look at this. Okay. So this is equal to 2 integral from -2 to 2. That's a 2. Maybe I will do that. So that's a 2 rad 4 minus x squared. Let's multiply the 2 inside. It'll make it actually nicer. Let's multiply the 2 inside. So the 2's will cancel, so you just get a 4 rad 4 minus x squared minus 2 times 4 is 8, so the 8's cancel, 1/3. And now let's peel off one of the 4 minus x squares. So there'll be 4 minus x squared times rad 4 minus x squared, because that will make things simplify. Hopefully, I think they will. And then the 2, oh, I shouldn't have done that, because this becomes, leave it as 4 minus x squared to the 3/2. Let's just leave it that way. And then times 2 becomes a minus x squared rad 4 minus x squared dx. So let's simplify this. So this is equal to integral -2 to 2. Now I can combine this first term and last term. So this is a 4 minus x squared times radical 4 minus x squared. So that's a 4 minus x squared to the 3/2. minus 2/3 of them, minus 1/3 of them gives me 2/3 of this. Okay, so let's integrate this. And let me actually give you a little bit of terminology. Okay, so let me try to integrate this. Again, there are several different techniques I could use, but I will use the pullback method. So use a pullback. I'm going to be using this terminology because it is useful. When I unify these concepts in the next week or two, and so I'm going to use a pullback. In this case, we call it a trigonometric substitution. Okay. So let x equal 2 sine theta. Okay. So dx equals 2 cosine theta d theta. And so now my volume is equal to, well, notice that sine of pi over 2 is 1. The sine of negative pi over 2 is negative 1. And so when x is equal to 2, theta is equal to pi over 2. When x is equal to negative 2, theta is equal to negative pi over 2. Okay. 2/3. Four minus 4 sine squared theta, replacing x here by 2 sine theta, the 3/2, times 2 cosine theta d theta. Okay, so this is equal to integral negative pi over 2 to positive pi over 2 of, well, some things can cancel here. So I can factor out a 4. The square root of 4 is 2. 2 cubed is 8. Oops. So, sorry about that. It blanked out for a second. I can factor out a 4. The square root of 4 is 2. 2 cubed is 8. Times 4 is 32. Over 3. 1 minus sine squared is cosine squared to the 3/2 is cosine cubed times cosine is cosine to the 4th. And so this whole thing just becomes some constant times cosine to the 4th. Okay, so now let me do a little bit of simplification here. So let's recall that cosine squared theta is 1/2 1 plus cosine 2 theta. Okay, so let's do that. And so this becomes 16. Well, this will be the integral, sorry. From minus pi over 2 to pi over 2. Well, this is cosine squared squared. So 1/2 squared is a fourth. 32 divided by 4 is 8. And then it's 1 plus cosine 2 theta. Maybe I'll do it squared. And then I'll simplify that. D theta. Okay. So let me multiply this out. So this is the integral from minus pi over 2 to pi over 2, 8/3 of 1 plus 2 cosine 2 theta plus cosine squared 2 theta, d theta. Now, of course, I'm going to use the same to simplify this part here. The cosine squared, I use the same formula. Okay, so this is equal to, I need another page. So this is equal to 8/3 integral from minus pi over 2 to positive pi over 2. 8/3. 1 plus 2 cosine 2 theta plus, now I'm just going to plug in to the same formula here. So this is 1/2, and maybe I'll write this as, multiply the 1/2 inside the parentheses. So this is 1/2 plus 1/2 cosine 4 theta d theta. Okay, just plugging in for theta here, 2 theta, and multiplying the 1/2 inside the parentheses. Okay, so this is equal to, so that'll give me a 3/2. So the integral minus pi over 2 to positive pi over 2, 8/3 this will give me a 3/2 plus 2 cosine 2 theta plus 1 cosine 4 theta d theta. Okay. Let me just look here. That's 4/3 plus 4. Okay, so let's integrate this. So if I integrate this, this is going to equal 8/3 times 3/2 theta plus integral of cosine will be sine 2 theta plus 2, no, I'm dividing by 4. Sorry about that. Plus, sorry about that, plus 1/8 sine 4 theta. Evaluated between negative pi over 2 and positive pi over 2. So this is equal to, okay, so let's see. 8/3. And let me just check something for 1 second here. derivative of sine is cosine 2 theta times 2. That's correct. Sine is cosine 4 theta times 4 is a half. Okay, so far so good, I think. So plug in pi over 2. So this is equal to 3 pi. Okay. So I'll do 3 halves times pi over 2 plus the sine of pi, which is 0. Okay. The sine of 4 pi, sine of 4 times pi over 2, the sine of 2 pi is 0. Minus, let's plug in minus a half. So that's 3 halves minus pi over 2. The sine of minus pi is 0. The sine of minus 2 pi is 0. So this is equal to 3/4 plus 3/4 is 3 halves. So it's 8/3 times 3 halves pi